Okay. So basically, so the task is Quora deduplication. So you have two sets of sentences, happen to be questions from Quora dataset.
I like when you understood what I meant by this.
Yeah, I'm your AI. Okay. Is this better? I can. Prefer to have it though. It does. Yeah, I prefer to have it. Okay, I hate you guys. Very opinionated. Okay, I close it. What you're talking about this? Oh, F11. Okay, yes, for sure. Sure. Okay, I'll do that. Okay, beautiful. So, all right. So that's a task. Two questions, and I wanna detect if they're duplicates or not, right? And here's what we need to do, simply at a high level, and then we get to the details. I'll definitely skip a couple of details, but don't worry about it now. First of all, I need some sort of vocabulary to start working with. If I don't have a vocabulary, if I don't have items, I need some sort of atomic pieces of text to use to start with. Okay, what are those? Here we're just using normal vocabulary. We're not talking. We're not using byte-pair encoding, which would be amazing, but it gets things even more complicated. Okay, so you have words, you have a vocabulary of 30,000. What do we use for the vocabulary, or whatever 1,000 words? We're using GloVe. GloVe has multiple types. We're using one of the GloVe pre-trained models. You already know what GloVe is. You know how it mathematically works. But as far as we're concerned today, is I want a dictionary where I input a word and it tells me an embedding. It gives me a representation for the word, and that's a vector I can start with. Neural nets work with vector as input and output, right? Because otherwise I can't compute anything. You cannot have neural nets to generate words. You can have them generate indices, right? Especially when you're generating, say, a text. And the one way you encode these indices is that you in your output layer, you look at the first, the leftmost element in your vector, output vector. You call it the index of it. You call it 0. The second one, the last one, n-1, n being the size of your vector, is the index of your last word in a softmax layer, and whichever you're predicting would be the could you mute me over there? Oh, thank you. And whichever you're predicting will be your no worries. Whichever you're predicting will be your index. So now you have to go from index back to word. So that's why the indexing. So you have so first of all you have your embeddings. Then, but to access these embeddings at any point in time, you need to connect indices to these embeddings. So it's not only good to use words. Word2Vec and GloVe take words and gives you they give you embeddings. Well, we want to make sure that if we give them an index, it'll give you the embedding. So you need that pipe as well. Okay, so that's one part. Then you start your neural networks. Just define your layers, write your layers. I could actually go, but let me do a quick and then verbal one, and I'll go through the network. You run through your layers, you run through your sequences, you add a bunch of dropouts, and then at some point, it's a binary classification task. At some point, you shrink it all down to one sigmoid. That's a number between 0, that generates a number between 0 and 1. So you get some sort of a vector. I don't know. You sum it up, then you run the sigmoid on it. It gets you a number from 0 to 1. If it's above 0.5, you can say they are duplicates. You can say it's 1. If it's below 0.5, you can say it's not a duplicate, it's 0. So that's everything you're doing. Somebody said something? Okay, so let me go through what happens here in the notebook. Okay, you're just getting the GloVe, the training set and your GloVe. So your training set just has Quora questions. you're importing regex, CSV, codecs for encoding, NumPy, pandas, all the good stuff. We created Keras for pre-processing just because it had it, and I apologize. We input a data loader and tensor dataset for tensor dataset for data loading practices and creating actual data sets. So when you're working with PyTorch, these frameworks, they have their own object. So you may have a NumPy data set. You may have an array is technically a data set. They exist, and I know it's annoying to have all these types doing the same thing, but they're not. They're classes, and their objects have methods that can be used, utilized over GPU, parallelized. These things you can do over a tensor. Sorry, you can't do over. You can't really bring a NumPy array to a GPU. It's just simply not supported. But on a torch.tensor type, you can bring it to a GPU, for example. So that's why they exist. But mathematically, they're the same thing. Okay. Anyhow, so you import your layer of the network. You input your NN neural net object. Your neural net object, you use it in the PyTorch pattern. You already went through the notebook. You know that there is a pattern. You got to initialize, define your layers, then you use the layers, right? And that's so in TensorFlow's defense, in TensorFlow 2.0, first of all, they created TensorFlow Eager. Everybody loved it. Everybody who already used, who hadn't switched to PyTorch completely by the time. Loved it, the TensorFlow Eager, so they made it default for TensorFlow 2. The problem with that is a good chunk of TensorFlow code is still in lazy mode. So right now, I can't recommend it. Right now, still, I think PyTorch is just far better, especially for the science agile loop again. Okay, so and you create this functional. If I'm not mistaken, this functional will give you the layers to use high-level layers. Okay, so you turn your text into a word list and you do a bunch of filtering on them. The reason for that is you don't want to have variants for different, like if I'm is actually 2 words, so you want to have I and am. And you don't want to have encode I'm once and then encode I once and then encode am once. Redundant. So a bunch of that's a good practice actually. So I told you that you can use this filtering as well to reduce your vocabulary size. Yep.
How come like something like a tokenizer or something in NLTK can't do something like what you did here manually? Like what if you missed a bunch of things? Like you have to go through your entire corpus to kind of figure out the patterns here.
You do, yes.
To get that. Okay.
Yes, you always do, because you never if you want to be thorough.
Yeah.
You can predict that some things, like you can have a list of function words and just, I mean, for deep learning, don't remove function words, but you can have preset lists that you can do, like things like these, like they're pretty common, and you can get away with that. There are these scripts out there. You can find a bunch on GitHub to pre-process for deep learning, and each deep learning application kind of has to do that if they want to do right by it. But if you want to be accurate, your text may have specific things, so but you're able to go to low level and do all that anyways.
Do you need also to correct any spelling?
The question is, so the previous question that I answered was, do you have to redo this pre-processing for every corpus or not? I said quite a big chunk of it you can repeat. The current question is misspelling. So your misspelling will end up be a word in your vocabulary, right? And that's bad. I understand. Hopefully your text isn't too bad that it's all this is a lot of misspelling, and in that sense you can ignore it, because finding misspelling is on its own a hard task. Unless you have a vocabulary, and you check with that vocabulary. And if it's out of that vocabulary, you say it's out of the vocabulary, so it's a misspelling. Let me get you the closest one. To do that, you need the edit distance. You get the minimum edit distance from it. But that's not recommended, because there are vocabularies, domain-specific vocabularies that you'll definitely miss. No dictionary. That's why Oxford gets updated every year. no dictionary has every word. Even Oxford doesn't have a lot of the colloquial words. It just doesn't. It can't afford to, because like the person who's writing it doesn't know that these people are using it this way. So I guess it's the trade-off. I prefer to not filter that out.
I've also heard that one way to augment text is to add in
To make it more robust. Yeah. So the comment was, you can even use misspelling to make your algorithm more robust if you're prone to be tricked by it. Yeah, absolutely. Okay, so you filter your text, and you're reading your training data. I think what I was asked, Ali, was I asked to go in detail every line, or just have an understanding, high level, on what each cell does?
High level is okay. Details of the architecture, like your
architecture, the neural nets. Okay, so I go high level here. So reading and training.
maybe a little bit.
Gotcha. So reading training data, it's important to know. So let me tell you. So your LSTM takes as input a fixed size vector. It's not capable of changing its input because it's going to rely on matrix multiplication down the line. That's why we use GPUs. They're good at matrix multiplications, much faster on a GPU than a CPU. But not every sentence is the same size of words. They're different size. What we're doing over here, if you have all the computation in the world, then pick your longest sequence and pad everything else. If you don't have all the computation in the world, most likely, one way is to pick a reasonable size, and it will affect if you're running out of memory, it could be that your size is just too big. You can shorten that size. Anyhow, that allowable sort of size of input vector. So you can truncate it. Let's say you optimize to do 50 words. We should have done it here. Let me see. 30, okay. Yeah, over here. So you allow 30 words. So if it's less than 30, you pad it, because there has to be something there. Your network can't just guess what it is. You're going to run into a programmatic error. And if it's greater than, you just truncate it to 30. That's what we're doing here. A good practice is to look at your data, see what the length is. You already know how to do that. The length, what the average length of the sentences is, and cover most of the distribution. Like usually to cover 90% of the distribution, again by Zipf's law, you need only half a size, something ridiculous like that, of the actual length. So a sentence of like 60, if we did it right, we didn't. I don't think we checked. But if you did it right, your length 60 will be something like less than 1%, or much less than 1%, like a very small decimal to even care about. So you have to truncate.
Yeah, I can check it later, but
yeah.
Do you know for padding, what does PyTorch put in by default? Is it zeros or?
I think you pad by zeros.
Okay.
Yeah, I'm not sure either. Yeah, you have to put a number in there, because you index.
Yes.
Yeah.
Like here, we're actually setting the max length to be 30, right? And like, does it actually make a lot of difference in your computation if you kind of just find the longest sentence in your document and just keep the max length to that, so that you're not essentially truncating anything in your document? Like if we had chosen max length to be 100 over here, would that make a lot of difference in computation? Does that?
It does, because you're so remember that you're numerous times and in parallel, if you're using some of these networks for RNNs, they're better. But remember, you got to bring back the gradients from your cost function all the way back to these embeddings, right? So the bigger they are, and if you have multiple sequences, usually how we run it, we run the RNN in parallel on multiple sequences. Your sequences get larger, and you may sooner run out of memory. And is it worth it? It's not, to be honest. That sentence that like 200, that's like such an outlier, you better miss it anyways. Yeah, don't worry about it. Unless in your case, like some sort of a medical detection task where you care about it, then you care about the outlier too. Usually in NLP tasks, they're not that important. So if you use the Zipsla, as I mentioned, you get like easily 95% of data by very much efficient, smaller size. So size matters these days. If you're using cloud, maybe not. Okay.
Thank you.
So yeah, absolutely. So pad, I think usually it's zero padding, but you can add any index. To be honest, it doesn't really matter as long as it's an index that's only used for padding. And then from there you get to your embeddings. For embeddings, we're already using Word2Vec. We know how it works. We're using glove, but we turn it to Word2Vec such that we can turn it into tensors. It's a little bit of a twist there, but don't be bothered by it. Glove is stored as text files. That's why we use Word2Vec to turn it into a Python object. And that's a very smart way, actually, to do it. But your vectors are still, they come from glove. The algorithm who trained it is glove. No matter what type of object we're using to store it. At the end, it's going to become a tensor anyway, but it's still a glove vector. So we load the pre-trained glove embeddings into PyTorch and just test if we got it right. Query the embeddings. Maybe I should have gone through the solution. Is it the solution? No, it's not. Okay, yeah. Anyhow, you have the solution, so maybe you can run the solution, see if it also runs out of memory.
Oh, I reran mine. It works.
Oh, it works. Okay. Let's see. Okay, good. So so here we concatenate questions. I told people who asked here the question, like you can go about it in a different manner. But one way to do it is you have this question, you have this other question, you just concatenate them, create a question, and then run it through, create a representation, a vector that has both questions in them, and then run it through your RNN and decide which class it belongs to. Okay, so here you're just creating the batch. You can't train everything at the same time, right? So you have to create batches of data. You get a few samples, both questions. So each sample is, each data point is 2 questions, right? That you vectorize this way. Okay. And you run your, so you concatenate the questions. You get your labels, and you turn them into a tensor. Blah blah, and you print a bunch of things out just to make sure. Let's see who. Okay, print a bunch of things out just to make sure you got it right. So when you're running PyTorch, no worries. When you're running PyTorch, it's super important to check all the time. Check your vector sizes. Especially if you're writing something from scratch or you're changing an algorithm. You always, that's why we print out these shapes all the time. Print out the shapes all the time. Every time make sure that these matrix multiplications work. For a matrix multiplication to work simply, they have to share a column and and what's the other thing? A row. Yes, thank you. I'm really tired. So the column and the row, they have to match in size, right? Anyhow, so always make sure. And that's like at least 50% of errors when you're writing TensorFlow code. But it's so hard to find them. Okay, anyhow, we split data into 80-10-10, train, validation, and test. And here's an agile advice. Never use your test set unless you're not going to touch that algorithm anymore, or you're doing a one-time report of performance to the business. If you use that test set for the second time, it's not valid. It's a validation set. It's not a test set. So what's the difference? Validation set, you separate it from training set, so your network never sees it. Okay, good. You can check if you're overfitting. But you cannot check for your biases. You look at the validation set, you go back, change things. So you are fitting to the validation set indirectly. Your network isn't seeing it, but you're seeing it, you inject your biases. Okay. The test results, when you're comparing actually all the systems for the last time, like validation set, you can use it for one system, for example. But when you want to compare systems, you got to use test because you want to take generalization into account. Now, if you use it once, next time you want to fix something, you're injecting your biases. So test set isn't valid test set anymore. So what if you think there are going to be scenarios that you're going to use test multiple times, you're going to select a few, check a few different methods multiple times, divide your test set into multiple test sets, and never run out of test sets, because that's the actual reliable. If you want to do things right, that's how you need to be doing it, right? Okay, so anyhow, so your test set, you use it only once. You can use test set only once. Yeah, okay, so that's, you create a torch data set by what you imported earlier. Okay, it's just dividing into your test, train, and validation sets. Creating the data set, creating your batch sizes. So for NLP, you can have big sizable batch sizes. Image you cannot. If you're especially if they're big images, if you can do 8, a batch size of 8, you're very lucky. That's just very like it's good. Usually, if it's lower, if it's batch size of 2, I can't. I don't know. I don't recommend it. Batch size of 4, okay, that's fine. But get your batch size up to 4. You want to have enough variance in each batch, because they will train your gradients, right? And when the batch size is smaller, you get a lot of those side effects. So it's important to regularize better. Okay. So you load your data, sanity check. Okay. Then your LSTM. Okay, so it tells you specifically what it is. So you have an embedding layer that gives you the embeddings. You have 2 hidden layers. In your LSTM, it's just a parameter when you define the LSTM, hyperparameter. You have a dropout layer, regularizes things. At the end, you have your fully connected layer. It's recommended to always add a fully connected layer because you can use your softmax to predict, or your sigmoid to predict right at the last hidden state. That's fine. You can still do that. What it makes you do is next time if you want to use that LSTM on another task, you have to retrain the last layer of the LSTM, which is harder than just train a fully connected layer. So you have to freeze everything over there, and if you're doing a fully connected, I mean, it also adds a little bit of a capacity to train, as opposed to just one last layer. Or I mean, you can. Training a fully connected layer is much simpler than running the second, training the second layer of an RNN. It's just more computationally more costly because it's an RNN. But in contrast, if you train your RNN once and capture all the text patterns, and then you switch tasks, and this time you're not detecting if it's duplicates. You're detecting. You want to classify the text based on the sequence. You just get rid of that fully connected layer and train that part. Only train the new fully connected layer. So it's important to have that fully connected layer. And then you produce a sigmoid, sum everything up, use a sigmoid function, get a value between 0 and 1, and say if it's a class A or B. Okay, here, so this is a PyTorch pattern. And TensorFlow uses this pattern nowadays as well. And I love this pattern. You simply just you inherit it from the NN module. It's a neural net module, and it has a bunch of things that help you. One is the initialization. So you initialize your entire network. So this is just initializing your entire network, all the other parameters, and then you define your feed-forward network. Like how define your forward pass. What layers goes first, for example. Everything is defined here, and well, you initialize your hidden layer as well. Weights, hidden layers, how many, so on and so forth. And you're taking them to CUDA. You're taking them. That CUDA command takes everything to GPU. That's why it's much faster. You can bring it back to CPU as well. Okay. So everything is and very very clear afterwards. So you're just setting a bunch of parameters, the output size of the network, embedding dimension, hidden dimension, number of layers, so on and so forth. And you use this LSTM model that you just defined with these parameters just to initiate your network. You're just initiating your network. You're not training. Now you want to train your network. So it's just say trainable, so it trains, forward propagation, back propagation, calculate loss, run the optimizer. Very simple. Yep.
Is there a reason why when you went from the LSTM layer to the dropout or fully connected layer, you only fed in the hidden layer or the hidden values? Or no, wait, it was just the output of the LSTM?
I think it gets yours. Or you're doing it on the output. You can do it on the output. We can do it on the hidden layer of the LSTM. Because you're, let me see, which one's computation more efficient? I think if you do it on the output, it's more efficient because you're not doing at each time step. Yeah. If you're using all of them, though, if you're using attention, then you have to do it every time step. Okay, so learning rate is this. So it's small. That's one of your hot parameters you can change. Criterion is basically your cost function. What is my cost function? Your optimizer, how you optimize, how you actually use your gradients to update the weights. That's your optimizer. And there are multiple methods to optimize. Adam is one of the best. I'm not going to go in detail, but ask me if you have questions. You define the number of epochs. For deep learning, 10 is fine. 20, 50 is, I'm comfortable with 50. And if you have compute, just the more the merrier. You make sure that you're running on CUDA, otherwise it's going to take a long time. And then for each epoch, obviously you train the network. Yeah, I think the rest is like pretty like self-explanatory. You just make sure things are in GPU at the right time. So these devices, these labels to devices, just pay attention to them. If you don't do that, if part of your vector is in CPU, it's going to become the bottleneck of your entire network, so it's going to slow everything down. It's very important to make sure everything is on GPU.
Excellent.
Yes?
For people who are new to Fiber, can you explain zero grad?
Zero grad?
Zero grad.
Yeah, okay, let me find it. Okay, yeah, so I think it just sets, it just sets your gradients to 0. So when you start the next, and that's some mistake a lot of people make. So when you start another epoch, you want to make sure there are no gradients, or even another iteration. You want to make sure you don't have gradients remaining from your past iteration, right? Okay. Right. So you don't want to add. So that's one reason actually you can run out of memory as well. If you keep the gradients, you can get these. Let me see. Well, you run out of memory if you don't zero out. You don't zero out, but you don't run out of memory, but you get vanishing or exploding gradients. More so exploding because they become so big. Or do you just use them? Let me see. If you don't zero them out, you will use the gradients from the previous step. Yeah, you got to zero them out. Yes. So so if you don't, you may keep copies, and you may run out of memory as well. That's fine. So I'm not entirely sure. Don't quote me, but I suspect that's the case. But regardless, you got to zero out.